Good afternoon, everybody. Today we will go through the 2023 February USACO competition Platinum level problem number 3. I know you guys are doing the March competition over this weekend. If you already finished, good luck. If you have not finished, hopefully this will give you some hint. So the problem number 3 is watching Cowflix. What this has is it has former Johns as a form, which looks like a tree, and then you can divide those trees into certain disjoint connected components, right? Then you can count the monies that you will pay for each disjoint component as the size of that disjoint components plus a constant of k. Okay? Bessie will be on some nodes of this tree. So those disjoint components need to cover every position where Bessie is on. Right? The question is, what is this minimum sum? Okay? Let's take an example here. So you have a tree which is 1 connect to 2, which connect to 3, which connect to 4, which connect to 5. And Betsy is at 1 and 5. So let's look at it. When k equal 1, the disjoint components, you can do this and this, right? So it's 1, size is 1, 1 plus 1 is 2, so it's 2 plus 2 equals 4. K equal 2, this is size is 1, 1 plus 2 is 3. 3 plus 3 equals 6. K equals 3, you can do 1 plus 3 is 4. And here 1 plus 3 is 4. So 4 plus 4 equals 8. Or you can connect this into one disjoint component. So it's 5. So it's 5 plus 3 is also equal 8. So when k equal to 4, you can do 5. So if you do this, single components, 2 separate, is 5 plus 5 is 10. Or you can do one component, which is size of 5 plus 4 equal 9. So obviously you don't do this, you do this. Same for 5. You take this as one component, so it's 5 plus 5 equal 10. So that's how you do it. So now, how do we do this problem? So there are a couple of different ways you can do this. But let's start with a simple one. Let's say, for each k, okay? Let's say for each k, let's say if I know k, right? If I already know k, okay, a fixed number. How do I find this number? So obviously you have a tree, right? So what we obviously want to do is want to try, can we DP it? So if I DP for each node I, right? So I have either this node, we don't want to have Bessie on this node, or want to have Bessie on this node, right? There's 2 possible conditions, right? So how do we calculate this? So dp of I of 0 is going to be equals infinite, right? If Bessie is actually on this node, right? Because if in this condition, if it says Bessie has to be on this node, so that minimum has to be 0 because it has infinity, because there's no way that it's not on the node. If it's on the node, if it's not on there, if basically cannot be on there, then you can sum, right, all the vectors which is child of I, right? So if this is your I, for each of your child, so you can sum up your child of there. If your child has something occupied, or child you don't have something occupied, right? So if the child, the Betsy has to be on the child, then this number, remember, is going to be infinity, right? So the obvious is that. If the child Betsy does not have to be in the child, you can still include it, right? Or don't include it. So for the same token, for dp of I of 1, it can be, so if dp of I is 1, so Betsy has to be here, okay? So if you don't have a child, if this child, Betsy, do not have to be there, then you do 0, right? So if Betsy has to be in here, you could potentially include it, right? So it's dp of u of 1, right? So just a second. Remember, if you include it, you have to add. So you build a tree, like you build a disjoint components like this, right? So remember, you extend the components. Remember, here you already add k, right? So you don't need to add k there, but you have to add the k on the outside. But remember, here is additional size, right? So the size extended. So it's k plus 1 plus this thing. So that is very simple dp. So now let's look at the complexity of this. You have, so you dp through this, right? So you have n, and then you have to do k of them, right? It says you have to find every k. So it's n squared. The problem says 3 seconds, and n is 1e5, right? So n squared cannot work. 3 seconds, 1.x of the default tells you what? Tells you n square root n is sufficient. Okay. You could try to do n log n, but n square root n itself is sufficient. So how do we do it at n square root n? Okay. So now here, I want you to come back to the USACO guide at the pattern level. Remember, we talked about divide and conquer, and we talked about square root decomposition. So divide and conquer, what does divide and conquer work? Is if you want to look at something, okay, let's say from A to B, okay? So if, we typically do from left to right, right? If between left and right, you can linearly extrapolate this value, then you're good, right? So everything can be interpreted. That can be done in the O of 1. Each one that can be done in O of 1. If not, you take the midpoint, then you do it, then you see you can extrapolate. So that is basically that. Then looking at the square root decomposition and go down to here, Moore's algorithm. Okay, I want you guys to look to, if you don't remember, read this moon on the tree, right? Then how do you handle a subtree query that or handle a pass query so that you can do unmarkup? Okay, so we will use that. Okay, so if you look at this case, if you look at the case here, original case here, I started with two disjoint. When k is 1, obviously you start with, when k increase, right? See, when k increase, you start to join the components together. At a certain level, you join, right? From 3, this is where you can start to join two components together, right? So that means when k increase, the disjoint components will connect together, right? So the size of the disjoint components will increase, the number of disjoint components will decrease. So size will either stay the same or increase. Number of disjoint components will stay the same or decrease, right? So if for here, so we need to track, if we track the size, okay, let's say if we have, so dp, so we have, let's see what we have, right? We have the dp, which is this value we're calculating, right, for each, right? Then let's say we take a dp2, which is the size of the components, right? Okay, so then we take dp3. Actually, we don't need the size. If you look, we just need a number of disjoint components I have under that tree. Okay, so when k increase, let's do divide and conquer on k. Okay, on k. So if I say I want to look at the k from left, from some value, left and right, if dp3, which is my size, is the same, okay? Sorry, my number of disjoint components is the same. Then so that means when I go from here to here, I don't change. The only thing I change is k, right? So that's a linear, that I can do it just linearly, right? So it can be done, each can be done in O1 time. It's like from here to here, right? So my number of disjoint components stay the same. I have two components, and each of them will increase by 1, right? Because only changes the k. Okay, so if left equal right, if dp3 at left equals dp3 on the right, right? So that is basically I can done linear, right? If not, then I take middle, right? Is divide and conquer, right? Left and right over 2. Then I iterate, right? So basically I do divide and conquer left and m. Then I do divide and conquer m and right, right? So that is O n square root n. Okay, so then that is basically using the divide and conquer, right, with then the read the moon on tree, it will explain to you why it is n square root n problem. Okay, so with that, because it is 1.5x, n square root n is sufficient. So this is actually a relatively simple problem to solve. You start with the dp, right? Then you figure out this restriction, 1.5x restriction means n square root n. And then the way to n square root n is to divide and conquer, because the reason because you can do that is because if left and right is the same, you can solve everything in between is just a linear of O of 1. Linear of O of right minus left, right? Each of them is O of 1. So it's basically O of 1 times left minus right. I mean, right minus left. You know what I mean. Plus 1 to be exact. Okay, so then you can solve this. Okay, so that use in the Platinum level USACO guide question, divide and conquer and square root decomposition technique. Okay, so good luck for your competition over this weekend, and we will come back next weekend to explain the solutions for this week's competition. Good luck.